Sometimes trying to keep up with tech, especially really complex stuff like databases, feels like you're just constantly chasing the next big thing, right? It can be a lot.
Oh, absolutely. Information overload is real. And that's exactly what we want to help with today. Think of this as your focus briefing on some key shifts in database tech.
Yeah, a way to cut through the noise.
Precisely. We've done a pretty thorough analysis of a range of material to pull out the really core ideas, the advancements. The essential stuff you need to grasp without getting totally swamped.
Okay, great. So this is our deep dive into different database approaches, the thinking behind them. Our mission really is to boil it all down, give you the vital insights so you understand the landscape and, why things are moving the way they are.
Right. And a good starting point is the rise of NoSQL. It didn't just appear out of nowhere. There were, real reasons driving it.
Like limitations with the older systems.
Exactly. Traditional relational databases, the ones with tables and rows, everyone knows they're solid, but, they started hitting walls, especially with, massive internet-scale apps moving to the cloud.
Oh, okay. So scale was a big factor? What else?
Well, data itself changed. It wasn't just neat tables anymore. You had all sorts of data structures. And then the demands for, super high performance, always on availability, especially across different data centers globally, that became huge.
That's right. The old model wasn't always cutting it for that kind of world.
And that's where NoSQL really found its opening. It offered different ways to tackle those problems. Apache Cassandra was a really significant early player here.
Cassandra, yeah, I heard a lot about that one. What was its big idea?
Its architecture was pretty different. Things like masterless replication, meaning no single point of failure, which is great for availability. It was built for global distribution from the ground up. And it had this promise of linear scaling. Linear scaling means, basically, add more servers, get proportionately more performance. Simple idea, very appealing. The key thing is Cassandra directly addressed those needs for a high availability and handling distributed data that modern web apps desperately needed.
Sounds like the perfect answer then, right?
Well, on paper maybe, but as deployments got bigger and more demanding, some challenges started to surface with Cassandra, especially around performance consistency.
Okay, interesting. What kind of challenges?
A lot stemmed from its reliance on the Java Virtual Machine, the JVM. Now, the JVM is powerful, but it can introduce these unpredictable pauses for things like, garbage collection. Milliseconds matter in high-performance systems, so these pauses, this latency could be an issue.
The dreaded garbage collection pauses.
Yeah, and also, it wasn't always the most efficient at using the latest hardware multi-core CPU's super dense SSDs. Sometimes felt like you weren't getting the full power out of your machine.
So, kind of an overhead from the JVM, and maybe not perfectly optimized for modern hardware. Was it tricky to manage too?
It could be, yeah, especially at scale. Ops teams often found themselves doing a lot of manual tuning, things like managing compactions, which is basically background data housekeeping and tweaking that garbage collection.
Sounds complex.
It often required developers or ops folks to have a really deep understanding of Cassandra's internals just to keep things running smoothly and scaling effectively. That's, a significant investment.
Okay, so that sets the stage for something new, and that's where ScyllaDB comes in, often mentioned alongside Cassandra.
Exactly. ScyllaDB positioned itself as a high-performance alternative, and crucially, it aimed for ancient and compatibility with Cassandra.
So you didn't have to rewrite everything?
That was the goal. Use the same drivers, the same query language, CQL, leverage the existing ecosystem. It's like swapping out the engine in your car for a much faster one, but keeping the rest of the car, Big efficiency gain there. Avoids a massive relearning curve.
Okay, that's a smart approach. So better performance without starting from scratch. What's its focus?
Low latency, data-intensive applications, the kind that need serious performance and need it reliably even when handling tons of data. And it gets there through some pretty fundamental architectural differences compared to Cassandra.
All right, let's get into that. What makes ScyllaDB tick differently?
Probably the biggest thing is its foundation. It's built in C++ using a framework called C*, and this enables what they call a shard per core architecture.
Shard per core? What does that mean in practice?
Imagine each CPU core on your server gets its own dedicated, largely independent slice of the database, its own memory, its own task queue. It's not the operating system constantly juggling tasks between cores. ScyllaDB pins its work directly to specific cores.
Okay, so each core is like its own mini database engine.
Sort of, yeah. The key insight is that this minimizes cores fighting each other for resources, reduces that expensive context switching the OS does, and really maximizes parallel processing power.
And because it's C++ there, not Java.
Right. No JVM, which means no unpredictable garbage collection pauses interrupting your requests. That's a huge factor for consistent low latency. Operations are asynchronous, uses clever techniques like scatter-gather for data fetching. It's all geared towards squeezing performance out of the hardware.
Makes sense. So what about memory management caching? You mentioned Cassandra uses the OS page cache.
ScyllaDB does it differently. It has its own application-level cache. This gives it much finer control over what data stays hot in memory. The result? Benchmarks often show ScyllaDB hitting millions of operations per second, with latency staying consistently down in the sub-millisecond range. That direct cache control is a real performance unlock.
Wow, okay. Millions ops per second, sub-millisecond, that's fast.
Does it offer other ways to manage different kinds of work?
Yeah, it has something called workload prioritization. This lets you tell the database how to treat different kinds of requests. For example, you can say, prioritize incoming user queries over background maintenance tasks like compaction.
So you can protect the user experience even when the database is busy doing background work. Exactly. Keep those critical path latencies low. And one more thing on the performance front, the drivers can be shard-aware.
Meaning they know which core holds the data.
Pretty much instead of hitting a random node that might have to forward your request, a shard-aware driver can talk directly to the specific shard, the specific core that owns the data you need. Fewer network hops, less coordination overhead, lower latency again.
So it's really optimizing that path from the application right down to the specific CPU core handling the data. Impressive. How does it scale?
It's designed for that linear scalability we mentioned with Cassandra. The idea is double the nodes, roughly double the throughput and capacity. It supports both scaling up bigger machines and scaling out more machines. Though achieving that lowest possible latency always involves making sure you got enough resources and minimizing data contention points.
Okay, fascinating evolution there from Cassandra's initial approach to ScyllaDB's focus on raw performance through architecture. But the NoSQL world isn't just these two, right?
Not at all. It's a really diverse space. We've talked key value concepts, but you also have major categories like document databases, think MongoDB, and columnar databases like ClickHouse, each suited for different kinds of problems.
All right, let's switch gears. Document databases. MongoDB is definitely a name you hear a lot. What's the core concept?
It's built around documents. Think of them as flexible containers for your data, often looking a lot like JSON. The big advantage is schema flexibility, or schema polymorphism as it's sometimes called.
Flexible schema, meaning you don't have to define everything up front like in a traditional database.
Pretty much. You can have documents in the same collection, like a folder, that share some common fields but also have unique ones. Imagine a product catalog. All products have a name and price maybe, but a shirt also has size and color, while a laptop has CPU speed and RAM. In MongoDB, you could just store all that varied information naturally in the same place without needing tons of empty columns for attributes that don't apply.
I see, so it adapts better to data that doesn't fit neatly into identical rows?
Exactly. And it's great for nested data, like you can embed the comments directly inside a blog post document or store multiple addresses within a customer document. For developers, this can feel very natural and often avoids complex joint operations you'd need in relational databases.
Seems very programmer-friendly. What else does MongoDB offer?
It has built-in features for scaling out called sharding to spread data across servers. It uses replica sets for high availability keeping copies of data, and it has a pretty powerful aggregation framework for doing analytics and business intelligence right in the database.
So flexible, developer-friendly, scalable. Any downsides or things to watch out for?
Well, that flexibility can be a double-edged sword. You still need to think carefully about how you structure your documents for efficient querying. Also, if you have very large documents and only need to update a tiny piece, sometimes the whole document needs to be rewritten, which can cause extra I/O. That's read-write amplification. And historically, transactions across multiple documents had some limitations, though they've improved a lot there.
Good to know. Where does MongoDB typically shine? What use cases?
It's popular for those product catalogs we mentioned. Yeah. Content management systems, consolidating data from different sources where the structure might change, real-time analytics feeds, things like that. Anywhere that flexibility in handling nested data is a big plus.
Okay, clear picture on document stores. Now, the other one you mentioned, columnar databases like ClickHouse, you said the storage is fundamentally different.
Totally different. Think about how data sits on the disk. Row-oriented databases, the traditional ones, and even MongoDB to an extent, store all the data for a single record together. Right? Row 1, then row 2, and so on. Right. Columnar databases flip that. They store all the values for column A together, then all the values for column B together, and so on. All the product names are stored in one block, all the prices in another block. That's the key architectural shift, column-centric storage.
Okay, why do that? What's the benefit of storing things by column?
Massive speed up for analytical queries. Think OLA, online analytical processing. Imagine you want to calculate the average price of millions of products. In a row store, you have to read every row, pulling in the name, description, SKU, and the price, even though you only care about the price. In a columnar store, you just read the price column's data block. Way less data to read from disk, way less I/O. Queries that scan or aggregate large columns are incredibly fast.
Ah, that makes perfect sense for analytics. Scan just the data you need. Is there a trade-off?
Yes, usually writing data can be a bit slower or more resource-intensive. When you insert a new row, you have to go and write each individual value into its respective column block on disk, instead of just writing one contiguous row block.
Got it. Faster reads for analytics, potentially slower writes. What's special about ClickHouse itself?
It's known for being a true columnar store, meaning really efficient, compact storage. It uses very effective data compression, and it can even do some aggregation work directly on the compressed data on disk.
Best use cases for ClickHouse.
It absolutely flies for data warehousing, business intelligence dashboards, real-time analytics on large event streams, log analysis, fraud detection. Basically anywhere you're crunching large amounts of data to find patterns or calculate summaries, increasingly used in AML training pipelines too.
Okay, so we've got ScyllaDB for low latency, high throughput, MongoDB for flexible documents, ClickHouse for fast analytics, quite a range. Now, underpinning all of this has to be security, right?
Absolutely essential. You can have the fastest, most flexible database in the world, but if it's not secure, you've got a huge problem. And a core part of database security comes down to two related but distinct concepts: authentication and authorization.
Right, auth and auxy often hurt together. Let's break them down. Authentication first.
Authentication is all about proving identity. It answers the question, who are you? It's the process of verifying that a user, or maybe another system, is who they claim to be.
How does that usually work?
Typically through credentials, something you know like a password or a PIN, something you have like a physical token, a phone app or a digital certificate, or something you are biometrics like a fingerprint or a facial scan. The goal is just to establish that the entity trying to connect is legitimate.
Okay, proving you are who you say you are. Then what's authorization?
Authorization comes after you've been authenticated. It answers the question, okay, now that we know who you are, what are you allowed to do?
It's about defining permissions and privileges. What data can you see? What actions can you take? Can you read, write, delete, change settings?
Got it. So authentication is getting through the front door. Authorization is which rooms inside you have keys for.
That's a perfect analogy. And you need both. They work hand in hand. You authenticate first, then the system checks your authorizations. They're both fundamental for managing users and controlling access.
And why is this maybe even more critical in the cloud environments we were discussing earlier? Because the attack surface is potentially much larger. In the cloud, access can come from anywhere, any device. So strong authentication, maybe multi-factor authentication, MFA, or single sign-on SSO through identity providers becomes vital to just verify who's trying to connect.
Makes sense. And authorization in the cloud?
Equally important. Cloud databases often hold really sensitive stuff. You need granular control over who can access what. This is where things like role-based access control, RBAC, or attribute-based access control, ABAC, come in. You enforce the principle of least privilege, only give users the absolute minimum permissions they need to do their job. This limits the damage if an account is compromised.
Okay, so how does ScyllaDB handle this? Authentication and authorization specifically.
ScyllaDB implements both. For authorization, it uses a whitelist model. This is important. By default, once you turn authorization on, nobody can do anything unless you explicitly grant them permission.
So it's locked down by default, secure starting point. How do you grant those permissions?
You use CQL commands, the same language you use for data. Specifically, the grant command. You can grant permissions like select, insert, create, alter, drop, etc. on specific resources, like a whole key space, a specific table, or even on roles themselves.
Roles, so you can group permissions together.
Exactly. You typically create roles like, say, app rate user, data analyst, administrator. Then you grant the necessary permissions to each role. Users are then assigned to roles. ScyllaDB also supports role hierarchy, so you can grant one role to another, letting it inherit permissions. Makes management easier. And of course, there's a built-in super user role with God mode access.
And you need both authn and authz working for things like auditing too, right?
Yes, precisely. Auditing relies on knowing who did what, so you need successful authentication and the authorization framework in place to log actions against identities and permissions.
Okay, access control covered. What about protecting the data itself? Encryption.
Yep. ScyllaDB offers encryption too, both for data at rest, meaning the data sitting on the disk, and data in transit data moving over the network.
Let's start with at rest. How does that work?
ScyllaDB Enterprise allows you to enable encryption by default for your data tables and also for important system data like commit logs and hint files. This is usually configured in the main scylla.yml file. It helps protect data even if someone gets physical access to the drives.
And the keys, how are they managed?
You need to configure a key provider. ScyllaDB supports integrations with major cloud KMS offerings like AWS KMS, Google Cloud KMS, and also KMIP compliant servers. Or you can manage your own keys if needed. You can also often override the default encryption settings when you create or alter specific tables, giving you fine-grained control.
Okay, so options for key management there. What about data moving between the database and the application? Encryption in transit.
For that, ScyllaDB supports standard SSL TLS encryption. You configure the ScyllaDB nodes with SSL certificates, and then you configure your client applications, your app code, your tools like Cassandra Stress with the necessary trust stores and key stores to establish a secure encrypted connection. Protects against eavesdropping on the network.
Right, securing the wire. Good. So multiple layers there. Now, running a powerful distributed system like ScyllaDB, it sounds like you really need to stay on top of maintenance.
Oh, absolutely. It's not a set it and forget it kind of thing. Proactive care is crucial for performance and stability. One common mistake we see is folks running really outdated versions.
Why is that such a big deal?
ScyllaDB development moves fast. New releases, both open source and enterprise, constantly include important bug fixes, stability improvements, and often significant performance gains. Staying reasonably current is key to getting the best experience and avoiding known issues.
How do you know when there's a new version?
There's a utility called Scylla Housekeeping that usually runs automatically and checks for updates, logging notifications. Plus, good monitoring dashboards will show you the versions running across your cluster. Generally, ScyllaDB supports the latest 2 major releases, so planning for regular upgrades is just part of the life cycle.
Okay, stay up to date. What's another potential pitfall?
Configuration drift. This is a classic distributed systems problem. Because each node runs somewhat independently, it's possible for configurations to become inconsistent across the cluster over time, maybe after an upgrade or replacing a node.
And that causes problems.
It can lead to really weird, hard-to-debug behavior. Maybe performance is inconsistent, or some features don't work quite right on certain nodes. Ensuring key settings, like the number of shards per core we talked about, are identical everywhere is vital. You usually need to rerun setup tools or use configuration management to enforce consistency, often with rolling restarts.
Consistency is key. Makes sense. Any other major maintenance point?
Monitoring. You absolutely cannot run a system like ScyllaDB blind. It produces tons of metrics about its internal state, performance, resource usage. You need comprehensive monitoring and alerting setup. It's your eyes and ears letting you see performance trends, spot bottlenecks, and catch problems before they cause an outage. Don't skimp on monitoring.
Sound advice. Now, we've talked a lot about running it yourself. What if you want someone else to handle all that operational stuff? Is there a managed cloud option?
Yes, there is. Scylla Cloud. It's their fully managed database as a service, or DBE. It runs the Scylla Enterprise version under the hood.
And the main benefit is,
Basically, they handle the operational burden, installation, configuration, patching, backups, monitoring, scaling. It's automated. Provision a cluster, connect your app, and focus on building features, not managing database infrastructure.
So ease of use, automated management. Does it promise the same performance?
It aims to deliver that same predictable low latency and high throughput, including those important 99th percentile metrics. They also talk about minimizing vendor lock-in, letting you choose the underlying cloud provider and
Interesting option. Okay, last area maybe, how do you actually measure the performance of these NoSQL databases? You mentioned benchmarks earlier.
yeah, evaluating performance is kind of complex. Standard benchmarks exist, but they don't always perfectly capture real-world enterprise workloads, which can be messy and unpredictable. But there are definitely key metrics people look at for facility.
Like, what are the main things you track?
You're looking at IOPS, input-output operations per second. Critically, read and write latency, especially the tail latencies like the 95th and 99th percentiles, because those represent the worst-case user experience. CPU utilization is important. Cache hit rates tell you if your memory's being used effectively. And, of course, disk, IWASH-O, and usage.
And how do you generate load to measure these?
A common tool is Cassandra Stress. Even though the name mentions Cassandra, it works perfectly well with ScyllaDB because of that API compatibility. You can use it to simulate various read-write or mixed workloads and see how the database holds up under pressure, generating those metrics we just discussed. One thing to remember, though, while ScyllaDB's architecture, like C-Star, helps isolate it from some OS-level noise, getting that peak
Tice.
performance still requires careful configuration and tuning based on your specific workload. It doesn't just happen magically. You still need to understand your application's needs.
Right, makes sense. Wow, we have really covered a lot of ground today from the whole evolution of NoSQL driven by a cloud and scale
To
needs,
diving deep into Cassandra and then ScyllaDB's architectural approach for performance.
then branching out to document databases like MongoDB with their flexibility and columnar stores like ClickHouse, built for analytic speed.
Hitting the crucial security aspects, authentication, authorization, ScyllaDB's RBAC, encryption at rest and in transit.
And finally, touching on the practicalities of maintenance, monitoring the cloud option and how you even measure performance.
Yeah, it's been a pretty comprehensive journey through this part of the database world. The goal really was to distill all that down, give you the key insights from our analysis, so you have a solid grasp of the different approaches and trade-offs. Hopefully, it's a valuable shortcut to understanding these powerful but complex technologies.
Absolutely. So, thinking about everything we've discussed, as you, our listener, reflect on your own data needs, your application requirements, which of these database styles, the high-octane performance of ScyllaDB, the adaptable documents of MongoDB, the analytical engine of ClickHouse, which one feels like it might be the best fit? And based on our dive today, what specific areas would you want to dig into even deeper next?